All right, hello everyone. How's it going?
Not
All
too
right.
bad.
Okay, we are going to start chapter 12 today, which is called multiple integrals. So if you look back at everything we've done up to this point, chapter 10 was about vectors. And we talked about vector, dot product, cross product. We talked about curves in space, right? Curves in space. And then we talked about, tangent vectors, velocity, speed, arc length, right? And then we transitioned from that into chapter 11, which had to do with partial derivatives and how we take derivatives of functions of several variables, and then how we could then use that to find local minimums and maximums and global minimums and maximums of surfaces, right? And that's kind of a very general overview of what we've done. And now it's time to get into the next part of calculus, which is integration, but now with functions of several variables instead of just a function of one variable, like we did in Cal 2. Good news is you're not going to learn any new techniques of integration. Everything you learned in Cal 2, there's nothing new in terms of techniques like integration by parts, partial fractions, all that. There's nothing new there. It's just now we're just gonna have to see how we implement that strategy of integration with surfaces and functions of several variables. So we'll start with chapter 12, section 1, which is called double integrals. In this class, we will do double integrals and triple integrals. So we won't go any further than triples, but theoretically, there's as many as you want. Just like with derivatives, you have first derivative, second derivative, third, fourth, fifth, sixth. Integration, same thing. So double integrals. So we're going to start out by first remembering in Cal 1, and I'm just going to breeze through this real quick. In Cal 1, hopefully in Cal 1, you learned about this thing called Riemann Sums. And the basic idea of a Riemann sum was that we wanted to estimate the area underneath the curve. And so we estimate it by drawing a bunch of rectangles and then finding a formula for these rectangles. And then what we do is we just put more and more rectangles in, and we just let the number of rectangles go to infinity. And that would give us the true area underneath that curve, right? That's the basic idea of the Riemann sum. And then we could construct kind of a picture. I'm sorry this looks so blurry. It just is not coming out very good. If we took this function and we wanted to estimate the area, what we did was we imagined that we had like a slice, this vertical slice right here, which is a rectangle, and we tried to figure out a formula for the area of one of those slices. And so we said, well, the width is the change in x. That's what we call dx, right? So the area will be the width dx times how tall it is. But the height of the rectangle should always just be the function evaluated at some point, x sub I, at some point in here. We just plug that value x sub I into the function. That tells us how tall we are. Of course, we need to know the function. Someone has to give us the function in order for us to do that. So this would be our f of x sub I. And that would be the area of that one piece. Now, to get the total area, what we did was we took a limit as the number of these rectangles went to infinity. And then the fundamental theorem of calculus tells us that this sum, this limit of this sum, is exactly this integral. All right. So I don't know how much your Cal 1 professor instilled this into your mind, but I want to make sure you understand this. This formula, the way that you should be interpreting this formula is this. This is the height of an arbitrary rectangle in here, right? This little rectangle, that right there. That's the height of it, okay? This right here is the width of the rectangle. And then the integral sign is telling you that you're going to take an infinite summation of those rectangles where they keep getting more and more narrow. And then the A and the B are your restrictions on the variable x. So that's your left endpoint and your right endpoint. So it's like you're sliding rectangles across this function, just across from A to B, and you're just adding them up as you go, an infinite number of them, and that's whatever this number is the area, right? Does that make sense to everyone? All right, well, we're going to move on. So let's see now how we're going to do double integrals and what they mean. All right, so let me clear this all out of here and go to the next slide. So what if we're trying to find the volume under a surface, not the area under a surface, but the volume under a surface using Riemann sums? So take a look at this surface right here. If we wanted to know the volume, so the yellowish orange is the surface. And if we imagine projecting that surface down to the XY plane, which is down here on the ground, then we're trying to find the volume of that bluish purplish stuff, okay? So the way we could do it is same thing as Riemann sums, but instead of trying to find the area of a rectangle, we can try and find the volume of these rectangular boxes. Now, the mathematical name for a box like that, a three-dimensional box, is called a parallelepiped. I don't know if you've ever heard that before, but that's what it is. So we want to find the volume of each of these parallelepipeds and then add them all up. And the more parallelepipeds we have, the more accurate we're going to be. So if I do more of those, notice this is going to change. See, I have more of those in here. See, if I do them even smaller cuts, I get more and more here. And it starts to approach the true volume, just like we did with the Riemann sums. And you can see we will have a little bit of error. Okay, my computer is slowing down. It doesn't like this. Oh, it doesn't like that. Trying to bring the surface in here. Yeah, it's hard to see it, but that surface, you can kind of see that we have error in here. The boxes are sticking up out of the surface. So we know that the sum is going to be an approximation unless we let the width and the width of those boxes go to 0, just like we let the width of a rectangle go to 0, same thing. So we need a limit of a sum, but to do that, we need an integral. But we actually need the limit of 2 sums. And the way you can kind of visualize that is what we're going to do. Let me back this up a little bit because this is slowing my computer down. Let me go back to like a really generic version here, just a couple of boxes. So what we're going to do is we're going to look at just, this box, this one, this one, this one, this one. So we're going to add those boxes up, and we're going to let those boxes get very narrow. And that'll be one sum, but then we also want to sum the next row, and then the next row, and then the next row, the next row. So we have a double summation, a sum in one direction, and then we have to sum across. So I have a better picture. I think this will help you see it. So what you're looking at here is our domain that's on the ground. So that's kind of like this picture looking from the top. Okay, you know what, this picture, let's do this one. So we're going to be cutting the domain into a bunch of little boxes, right? And so if we look at one box in particular, the width of it this way is our change in X, and the width of it this way is our change in Y. And so if we want to know the volume of this box, one box, if we want to know the volume of one of them, it should be how wide it is, right? Times this kind of depth. And that's our change in X and change in Y. So that's where that comes from in the formula, change in X, change in Y. And then all we need to know is how tall it is. And the height of it is going to be the function's value at that particular point, X sub I, Y sub I. And that right there, that point is just any point in here. And then what we do is we sum that up. So we have this double summation. Sorry, this should be J here, not I. And so we want to sum those up. and let the number of them go to infinity. So what you get is a double integral where you have this inside the integral. So f of xy, that's some point inside, that's going to give you the height this right here is the height of the box, and then this is one of the widths, and then this is the other width, or let's just call it the depth. So again, the formula here is that what's in here is just the formula for the volume of one of the boxes, and then the double integral allows you to add them up in both directions. Does that make sense? Does the formula kind of make sense as compared to the traditional Cal 2 integral formula? Are there any questions about that? Just ignore this. I accidentally copied it twice. Actually, I could probably delete that. Okay. All right, so let's get to the formula. We're not going to do Riemann sums. Like, we're not going to do them by hand like we did in Cal 1. That's a pain in the ass. All right, so now the definition. The volume between some surface f of x, y, and the xy plane, which is z equals 0, over some rectangle. Notice how we write a rectangle? We write in brackets AB. It's not a cross product, but we use that symbol, cross CD. So this is always going to be your restriction on x's. These are your x's, the x restrictions, and this right here are your y's. The way
Sorry,
we
what does the cross mean again?
It just means you're taking those two intervals. Like here's AB, and here's CD. And so this is the way we represent all the points that live in that box. That's just the way we notate it.
Oh, so it's like no special meaning to it.
It's not like a computational thing, like a cross product formula or anything. It's not like that. It's just a notation to represent that interval crossed with that. The way you can look at it is this is the interval AB, right? And it's almost like this is the interval CD. And it's almost like if we're talking about this, then you're almost like taking that and multiplying it by that. But that doesn't make any sense. To multiply intervals doesn't make sense. But that's the notation we use for it. Mm-hmm. And this is called capital R. That's our region, okay? So back in Cal 1, remember in Cal 1, when we're doing the area under a curve, right? When we're doing the area under a curve in Cal 1, our integral goes from A to B, right? So our interval is just AB. Here, because we're talking about a two-dimensional region on the ground, capital R, this region is going to be some interval for X and some interval for Y. So the notation, and let's start paying attention to this, because notation is one of the things that's going to become very difficult in this class as we proceed. There's so many formulas in here. We need to understand what every piece of the notation means. So first, double integral, right? We have a double integral. And this is our region. The R is subscripted below. And then we have the function, the surface that we're integrating right here. And then notice D capital A. D capital A. You know, back in Cal 1, the formula was very simple. It's integral A to B f of x dx, right? And dx represented the width of the rectangle. Here, dA is like the infinitesimal little area of that patch on the ground. So dA is this piece right here. I know I've got quite the mess here. This right here, that's dA. It's this little rectangle patch on the ground. So that's our new notation to represent the volume under some surface. Now, if you start to plug in specifics into this, dA gets replaced with dy dx. Okay, that was the width and the depth. And then our limits of integration go from A to B and then C to D on the two different integrals respectively. Now, you can write it this way, or equivalently, it's the exact same answer, is if you write the same thing, but notice you switch the order here. So if you switch the order there, then notice that these switch orders. Okay, so where you put the limits of integration switch orders if you change the order in which you're integrating with respect to. And I like to look at it this way. You have an inner integral, like this right here is like the inner integral, and then you have the outer. So notice that if dx is on the outside, then the limits are a and b, because those are restrictions on x. And if dy is on the inside, then your restrictions are c and d. Those are your restrictions on y. And if you switch them, then dx is on the inside, then you put the ab here, dy is on the outside, so you put the cd there. Now, this is just notation. I haven't shown you how you actually do one of these. This is just purely a notation thing at this point. So I think it's time for us to try and that's me just saying same thing, inner and outer. Let's do a problem, and then you're going to see how we do this. So find the volume underneath this surface on 0, 2, 0, 2. So I'm going to show you the picture of what we're doing first, and then we'll actually find the volume. Okay, so here we have the domain, right? That's the domain. That's everything on the ground between 0, 2 and 0, 2 for x and y respectively. And then we have a surface, right? We have the surface that is above this domain. And what we're trying to find is the volume underneath that, right? So we're trying to take everything in this square and kind of project it up to that surface and drop down all the points below to get that volume, right? That solid underneath here. We're trying to find the volume of that. Does it make sense geometrically what we're looking for? The volume of this?
Yeah.
Okay. So let's find the volume. And to do that, we're going to take this to another page here. All right, so we have our surface. Okay, our surface is defined. We have our restrictions on x. These are our x restrictions. This is our y restriction. And so what we're going to try and do is do the double integral over the region R of this function of x and y with respect to area. With respect to area. That's the way I'm saying this now. With respect to area. So that's the general formula that will give us the volume. Now it's time to plug in the specifics. I'm going to do the outside. I'm going to do the x's. So my outer integral, look at the way I wrote it. 0 to 2. I'm using this 0 to 2. And I put dx on the outside. And then I have an inner integral, which I'm actually going to put in, well, you know what? I'll do it next up. Then I have the inner integral, which also goes from 0 to 2. And that's going to be my restrictions on y. So that's going to go here on the inside. And then I have the actual surface, which is 16 minus x squared minus y squared. And that's it. Any questions on that notation?
It's minus 2y squared.
Oh,
Yeah,
I
I was gonna say that.
Sorry about that. Thank you. 2y squared. All right, so how do we do this? Well, we're going to do this integral first. We're going to do the inner one first. All right. So we are going to be integrating with respect to what variable on the blue one? What are we treating as the independent variable?
Y.
The y, right? So remember in the previous chapter, if we wanted to do partial derivatives, we had to let one of them be constant, right? So if we want to do the partial with respect to x, we had to treat y like a constant. If we wanted to do the partial with respect to y, we treated x like a constant. Well, integration works the same way. if we're going to integrate with respect to y, then we must treat x as a constant. Okay, x constant. Now, when we do it with respect to x, then we would treat y as a constant. All right, but you'll see that won't matter. Okay, so let's do this inner integral first. So watch the way I'm gonna do this. I'm gonna go 0 to 2. That's the outer integral. And then in brackets, I'm gonna take care of the inner one. Okay, so now the blue part. What is the antiderivative of 16 with respect to y?
16y.
16y. Okay, so 16y minus now the antiderivative of x squared. So just treat x like a constant. So let's just say this was like minus 10. Then what would the antiderivative of minus 10 be?
Minus 10y.
Minus 10y, right? So here I'm going to say minus x squared y. That makes sense? What about the last one?
3.
Minus 3. Oh, minus 2.
2/3 y cubed, right? Because here we're just using the power rule for antiderivatives. So the fundamental theorem of calculus says that when we're doing an antiderivative, we do the antiderivative of each piece, right? Boom, 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 got that. And then we're supposed to put this evaluation bar here, right? And those are where we put our limits of integration, right? Now, in the past, we just put the numbers here, didn't we? Like if it was from 0 to 2, we put 0 to 2 here, right? But now that we have two variables, I need to be very clear on what it is we're replacing with 0 and what it is we're replacing with 2. And since we integrated with respect to y, that means we are going to be replacing y with 0 and y with 2, not x. We're leaving x alone. So from here on out, you will see me putting letters here next to the numbers that we're plugging in. This becomes even more important when we have 3 variables later. Okay, so integral, let's see, 0 to 2. Let's go ahead and do this. Remember how fundamental theorem of calculus works, right? You plug in the stuff for 2 first, and then you plug in the stuff for 0. Right, so this stuff goes in first. So if I replace all my y's with 2, see what we get. 16 times 2 is 32. Let's see, minus x squared times 2, that's minus 2x squared. And then if I replace this with 2, I get 2 cubed, that's 8. Times 2 is 16, so I get minus 16/3. Is that all right? Now just plug in 0. Well, that's easy because that just kills them all off, right? 0 here, 0, oh, sorry, 0 here, 0 here, 0 here, everything's 0. And let's look what we have now. We have integral from 0 to 2, and then we have 32 minus 2x squared minus 16/3. I guess I could put the 16/3 and the 32 together, couldn't I? I could do that. What's that? 96, was that 80/3? I believe. Multiply that by 3, 96. Yeah, 80/3. We good? Okay, now we're back in Cal 1. I mean, sorry, Cal 2. Now we're, well, this would be a Cal 1 problem at the end of the semester, maybe. Okay, so now we're back to basic integration. So we do the antiderivative now with respect to x. So the antiderivative of 80/3 is 80/3 x minus 2/3 x cubed. And we're evaluating this from x equals 0 to 2. And now we just plug in 2 for x. So if we plug in 2 for x, we get 160/3 minus 8, 16/3. And then minus, now we plug in 0 for x and we get 0. So what is that, 144/3? There it is. There it is. So this new idea, right, of doing a volume underneath the surface, there's really not any new like calculus involved. It's just a matter of applying the formula properly. Are there any questions?
Okay, this might sound like a dumb question because I'm sure I'm supposed to remember this from Cal 2, but is there something that you're supposed to do with the constants? Because we've lost the constants.
Okay, good question. This is a definite integral,
Right,
so you don't have a constant of integration. You're talking about like a plus C, right?
right. No, that makes sense. That
Yeah.
makes sense because it's on a closed, okay.
Yeah, because it's a definite integral, we have limits of integration. We're going to have just a finite number. Good. All right, so let's look at the next thing. How about this one? So using slightly different notation here, find the volume under this surface. And here the restrictions on X are given and Y are given. So it's not given to you in that like bracket form with the cross in between. It's just a different way of writing it. So this is just to show you different notation. So we want to find the double integral over the region R of f of x, y with respect to area. Now, it might be worth it for us to draw the region. X is going to go between 1 and 2, and y is going to go between 0 and pi. Pi's up here somewhere. So we're talking about this region here. Right, that's R. So we should be able to do this same way we just did the last one. Let's go 1 to 2. It's going to be my dx. And then the integral is going to go from 0 to pi. That'll be my dy. And then the inside is going to be the actual function. Questions on the setup? Start out with this inner integral. Let's do that first. So we're going to have integral 1 to 2, and then here comes the antiderivative. We have to figure it out, and then dx. All right, this antiderivative is not as clean as the previous one, because we're going to be treating x like a constant, right? X is constant at this point. So I think it might be worth it for us to look at that integral over here by itself. That's what we're trying to do. How would you do that integral? Just imagine that x is a constant. Let's just say x is a constant. Let's just put 5y here. Okay, I know it's not 5, it's really x, right? But maybe if you look at it this way, it might help you see how you would do it.
I feel like I'd do it by parts.
Integration by parts. We need to do integration by parts. Now, this again is going to go back to your method, the way you learned it, the way that I teach it. I do a table, I do u here, I do dv here. And in this case, because if I let u be y, then I know it's going to go away when I differentiate. And that means this is going to have to be, and be careful here, it's going to have to be sine of xy dy. I'm out of room here. Yeah, I'm going to put the x back in here. Just remember that x is a constant. So once you've got this, I'll move it over just a little bit, give myself more room. Dy, yeah, be careful, it's dy, right? So when I fill out the table, I differentiate down, and that gives me dy, and then I integrate to come up. The antiderivative of sine of xy with respect to y would be, careful,
Negative cosine of xy over x.
negative. So negative because, yeah, because it has to be, right? I'm going to write it this way, negative 1 over x cosine of xy. You need the negative there because the derivative of cosine of something is negative sine. And so you need it to be positive, so you have to have a negative out there. And then the 1 over x is to take care of the chain rule. Because when you take derivative of the inside with respect to y, you get an x to pop out. So you need that 1 over x out here. Are there any questions on that?
No, pretty straightforward.
Okay. And now, according to the integration by parts formula, this will become these two multiplied. So I'm going to write that as negative y over x cosine of xy. Okay, ultraviolet. And then minus the integral of these two multiplied, the diagonal. And I can, yeah, I'll just write it, negative 1 over x cosine of xy dy, which is negative y over x cosine of xy plus the integral of, plus, I can bring the 1 over x out. Why can I bring the 1 over x out? I thought you weren't allowed to take x out of an integral.
The constant.
Because it's a constant.
It's treating it like a constant, so we can bring it out. And now we just find the antiderivative of this. At any point that you need me to clarify what I'm doing, please just stop me and say, hey. Okay, so let me see, plus 1 over x times, all right, now the antiderivative of that should be another 1 over x, but this time sine of xy. Now, Margie, here we would have an integration of a plus c, we would, but remember, we're about to do a definite integral. So I'm just going to take this answer and plug it in here. This is negative y over x cosine of xy plus 1 over x squared sine of xy. And we're going to evaluate this from y equals 0 to y equals pi. Maybe I should have given myself a little more room there for that antiderivative. I keep going.
I feel like this is gonna lead into us having to use the other one where we switch the two, the inside and the outside.
Maybe. Let's see. Let's see. No one's brought that up yet, Adam. So I think you're on the right track here. Maybe. We'll see. I think we might be able to get this. We're about to find out.
Well, it would make it more simple.
Oh, definitely. Definitely. Okay, so here's what we're going to do first. We plug in pi, we see what we get. We plug in 0, we see what we get. And then whatever that is, we'll go dx. Okay, so if pi goes in for y, just remember it has to go in for y. We're going to get negative pi over x cosine of, let's see, pi times x, pi x, plus 1 over x squared, and then sine of pi x, right? Y'all agree with that? That's just pi going in for y. Now 0 for y. Okay, that's good because that goes away. 0 over x, that's 0. And then if we plug in sine of 0 would be 0 also. So that's all 0. So at least we're somewhat happy about that. Would y'all agree? Somewhat happy?
Yeah.
Okay, equals integral 1 to 2. All right, the only thing left in here is negative pi over x cosine of pi x plus 1 over x squared sine of pi x dx. Oh, shit, right? So you look at this now and you're like, all right, now we've got to integrate this with respect to x. I have a plus sign, so I can do them individually. But this is going to require probably an integration by parts. And this one's also going to be an integration by parts. And this is starting to look like a disaster. Now, could we do it? Yes. But Adam brought something up, and I was hoping someone would mention this when I first wrote the problem down. I did integral 1 to 2, and I put dx on the outside, I put dy on the inside. Question should be, do we always have to do it that way, or can we do the 0 to pi on the outside and do the 1 to 2 on the inside? So can we switch it? Are we free to do that? And does it make the problem any different, right? So what I'm going to do right now is, like I said, I'm going to say, oh shit, and I'm going to just stop here for a moment, because this is starting to seem like a lot more work than I want to do. And I'm just going to take the original problem again. I'll take this one, then we'll just go to a new page. You don't have to say shit too. If that bothers you, you don't have to say that part. Okay, so I'm going to take this and I'm going to say, okay, question. Can I just do this? Can I just make this 0 to pi dy out here, and then go 1 to 2, and then y sine of xy, and do the dx on the inside? So this is a question. Can we do this? Does it make it any better? So we'll leave it as an open question. Can you do it? All right. And let's just see if it makes it easy. So let's see about making it easier. Now we're going to go 0 to pi. Okay, here comes the antiderivative. Okay, now I'm treating y like a constant, right? Y is a constant. So when I do the antiderivative of this y on the outside can just come for the ride. And then I'm just finding the antiderivative of that with respect to x, right? Which would be what?
-1 over y cosine of xy.
-1 over y cosine of xy. So again, the antiderivative of sine of something is negative cosine of it. But because of chain rule, you have to scale by -1 over y so that it'll kill off the y that's going to come out of here when you differentiate with respect to x. And we're going to evaluate that where to where.
From x equals 1 to x equals 2.
X equals 1 to x equals 2. All right, we'll figure out what that is, and then we'll integrate with respect to y. Let's see if this gets any better. Hey, wait a minute, don't those y's cancel? Those y's cancel, don't they?
Yeah.
All of this just becomes -1. Well, that's nice. Okay, this becomes integral 0 to pi. And then now inside here, I'm going to plug in my two things, and then dy will come later. And so when I plug in 2 for x, I get negative cosine of 2y. And when I plug in 1 for x, I get negative cosine of just y. Which means I have integral 0 to pi of negative cosine of 2y plus cosine of y dy. And I don't know about you, but this looks a lot better than the last integral, doesn't it? I can integrate both of those with respect to y very easily. Well, I hope we can all do that. This should just be, okay, antiderivative of negative cosine of 2y should be -1/2 sine 2y. That's antiderivative, plus just sine y here. And we're going to evaluate that from y equals 0 to pi. This doesn't seem right. If we plug in pi into this, what do we get?
You're just going to end up with an
0.
answer 0 at the end of all of it.
0, don't you? Sine of 2 pi is 0. Sine of pi is 0. When you plug in 0, you get 0. This whole answer is going to be 0, isn't it? Man, did we mess up? Questions? We have 0 as an answer. Did we mess up? Well, let's see geometrically what we just did. We were looking at this domain, right? We were looking at that domain, and we were saying, okay, what does the surface look like above this thing, right? Well, here's the surface. You ready to see it? This is the actual function that we were talking about here. This right here. Let me graph that for you. There it is. Cool looking surface. And we were trying to find the volume between that surface and the XY plane. So here comes that solid. Here it is. Okay, it's kind of hard to see it there, but let me pull the surface out of here. And there it is. So guess what? Some of it is above the XY plane and some of it is below the XY plane. And just like in Cal 1, if you even if you took, let's say, like the sine function, if you were to integrate from 0 to 2 pi of just the sine function, you would get 0 because it counts the area above the x-axis as positive and the area below the x-axis as negative. So that's exactly what happens with the double integral also. Any volume that is above the xy plane is counted as positive. Any volume that's below is counted as negative. And in this particular problem, this one in particular, it turns out that the volume above and below are equal. And so they wipe each other out. And that's why we got 0. All right. So there's 2 kind of main points to this problem we just did. The first point is the order which we do this does have an impact on the difficulty of the problem. And here, I guarantee if you continue this problem, you would get 0 if you could do the integration. All right. But it was much easier to switch it, right? We still don't know if we can, but if we're allowed to, then the answer, this was a little easier. So that was the first thing. Order does make a difference on the integration. And then the second point that's important is that volumes above the x-axis are positive and volumes below are negative. So you have to always keep that in mind, that when you get a final answer, there may be something on the bottom that's contributing to like taking away from the volume. All right, so let's answer the question, are we allowed to do it, right? Are we allowed to actually switch? Well, you have this thing called Fubini's theorem, okay? And it says that if F is continuous on this rectangle, so you have some region on the ground that is a rectangle, right? That region is a rectangle. It's X is between 2 constants, Y is between 2 constants. Then you're always free to switch the order of integration. Now, this is a theorem, which means it has been proven. All right, we are not going to prove it. All right, so what we did in the last problem was okay. All right, so this problem says to verify Fubini's. What did I say? Fubini? It's Fubini. It's not Fubini's. I typed this in wrong here. We'll just leave it because that's kind of fun. Fubini's theorem. Okay, so this one says to verify the theorem. So that what all this means, and we're not going to do this problem, is set up the integral doing the dy on the outside, dx on the inside, figure that all out, and then do it reversed, and then you should get the same answer both ways. But because of time, I'm not going to do that. It's actually a pretty easy integration because these are just both power functions, so there's no integration by parts. It's pretty straightforward. Now, we do have a very special case when it comes to double integrals. And this will come up later on in the class, and you'll see me use this, and it's just going to be it's a shortcut, okay? So if your function of x and y, if this surface happens to be some function of x times some function of y, then if that's the case, you can take that double integral and you can break it up into an integral with respect to x, g with respect to x, and then multiply that answer times the integral of h of y with respect to y. You just multiply those 2 answers. Let me show you an example of what this is saying. So let's look at this one. All right, does everybody see that in this problem, you have some function of x here and some function of y here, and they are separated by multiplication, right? See that? Now, look at the previous problem we did. See this problem here, the one that we just did a second ago? Do y'all see that you can't write it that way? Like this sine of xy has both x and y in it. You can't write that as two functions separated by multiplication, one of them having only x's, the other one having only y's. How about the first problem we did? This one right here. Can you look at this one as some function of x times some function of y? No. You can say it's some function of x minus some function of y, but not multiplication. In the special case that you do have a function of x times a function of y, here's what you can do. You can take the double integral over that region, the rectangle, of the surface with respect to area, and you can break it up into the integral. Let's see, let's do the x first. So x, the x function is the sine function, so I'm gonna go sine. And then I do my restrictions on x here, 0 to pi over 2. Then times whatever I get if I go from, let's see, my restriction on y goes from 0 to pi over 2. And then it's the y function, so cosine y. So those are two problems we could do. Separately, we just go and we work that out, we get a number. Then times, we work this out, we get a number, and then we multiply those two answers together and we get our number, and that's the answer. So you can break a double integral down into two single integrals if and only if they are functions of x and y separated by multiplication. I'm not going to work through those. I'm just going to assume you know how to do those two. Okay. Here are some properties of double integrals. Just they're properties that you may assume are true, but now I'm telling you, yes, they are. If you want to do the double integral of some surface plus or minus some other surface, that you're allowed to split this into two double integrals. That's just the way integration worked in Cal 2, right? If you want to do the integral of a sum or difference, you can break it into the sum or difference of two integrals. Same thing with constants. If you have a constant inside a double integral, the constant can come out. Okay, so that's the same thing we've seen in the past. This next property, I think, is intuitively clear. If you have some surface, f of x, y, that's always bigger than or equal to some other surface. That means you have a surface f that is always above some surface g. Well, they might touch somewhere, but f is always above or equal to g. Then the volume under f must be bigger than the volume under g, because the f surface is always above the g one. So you're going to have more volume under the f than you would the g. All right, so now let's use this to try and figure out a reasonable way to find the volume between two surfaces. So back in Cal 2, think again. In Cal 2, we started out with the function f. We went from a to b, and then we said that the area here would be integral a to b f of x dx. And then after that, you say, okay, well, what if you have a function f and then some function g, and you want to find the area between them? Then that area would be the integral from a to b of the top function minus the bottom function. You all remember that from Cal 2, the idea of having like a top function and bottom function, you just subtract the two to get the area between? Same concept here. There's nothing new. If you have a surface, two surfaces, f of x and g of x, sorry, f of xy and g of xy, and they're both on some rectangular region A, B, C, D, then the volume between them is simply the f function minus the g function. That's it, the double integral. What I think is cool is looking at the picture. You have the region on the ground, okay? That's your region on the ground. Then you have the g function, which is going to be this bottom red surface. And then you have the f function, which is this top surface. And you're trying to find the volume between them. So you're essentially first looking at the volume under f, which is everything down all the way. That's the volume under f. And then you're subtracting from it the volume under g, which is everything from g down. And that would give you what remains in between the two.
Sorry, I think I should have asked this before, but whenever we get a equation where it equals to 0, the double integral, and it has the positive and negative volume, you know, under and above, would we need to prove that, or is it just acceptable that it's 0?
Accepted at 0. In fact, determining in that problem that I showed you where part of it was above and part of it was below, if you were asked to find, hey, well, how much of it was above? That would have been very difficult to do.
Mm-hmm.
Actually, we don't have a way of doing it right now. We could do it maybe in the next section, but not right now.
I had a
Okay.
question.
Yeah,
So say the function of f of xy is easier to do with like dy before dx, but the second one that we're subtracting is easier to do f dx then dy.
mhm.
That's still equivalent, right?
That's right, because you could split it into two separate double integrals and then do each of these double integrals can be done in either order, right? So you could do this first one with dx dy and the second one dy dx. Or if you want to do them both the same, like dx dy, you can put them together into one double integral and then do it all at one time, which is usually preferred because you kind of like only have to do the integration one time as opposed to do, well, yeah, each variable once. Here you'd have to do each variable twice. But yeah, you can do it. You could do it separately if you needed to. Okay, so that's actually it for this section. All right. You'll see when you do the assignments here, they're not that bad. All right. And that's because when we do double integrals over rectangles, right? All these regions on the ground have been rectangles. Double integrals over rectangles is easy. 12.2, next section, is where things started to get a little more complicated because we don't always want to be restricted to rectangles on the ground. So that's what the next part is about, 12.2. Double integrals over general regions. Here's where things start to get strange. Not strange, but they're just more difficult. So we've already seen that when our rectangle on the ground looks like this, everything's pretty straightforward, right? Then we have a rectangle, we can do the volume between two functions, right? Doesn't matter, right? Sorry, this is the same picture twice, let me delete that. So we've already seen that we can do that pretty easily. We can even switch the order of integration, dx dy or dy dx. We're free to do that. However, what if our region on the ground is not a rectangle? We are going to focus our attention right now on two different types of regions that we could have on the ground. The first is called a type 1 region. And type 1 regions look like this. X is stuck between two constants, and y is stuck between two functions of x. That's a type 1 region. So y is trapped between two functions of x, and x is trapped between two constants. Here's an example of a type 1 region. So notice that in this yellow region, your x's are always trapped between a and b, right? X is always trapped between a and b, but your y values are stuck between that curve and that curve. So we have that the y is smaller than some g function, g2, and always bigger than some g1 of x. Do y'all see that? So the y's are stuck between two functions of x. The x's are stuck between two constants. That's a type 1. When you do a type 1 region, if your region on the ground is type 1, then the volume underneath the function we will write as the double integral over d. D here standing for domain, where the previous R was a rectangle, right? Capital R was a rectangle to let you know, like, hey, it's a rectangle. Generally, though, we put D there to represent some domain. So if we're looking at a type 1 region, then you must do outer integral must be with respect to x, inner integral must be with respect to y, and then your limits of integration are these restrictions. You are not, I repeat, you are not allowed to change the order of integration with a type 1 region. The constants must always be the outside integral, which means that x is always the outside. Okay? Now, if we have two surfaces, F and G, and we're trying to find the volume between them, then it's the same thing. We're just going to subtract the two, but we still have to do the order of integration properly. So there's no better way to understand this than to just do an example. Find the volume under z equals x plus 2y on the region bounded by y equals 2 x squared and y equals 1 plus x squared. We'll look at the picture after we do it. Take a moment right now. I'm gonna go refill my drink, blow my nose because my allergies are bothering me. Wife had me in the yard doing yard work yesterday. It was too windy to be doing yard work yesterday. It's blowing everything around. See if you can at least draw the region, okay? Try and draw this region. I'll be right back. All right, hopefully you're able to draw these okay. Y equals 2x squared is a parabola that opens up, goes through the origin. Y equals 1 plus x squared is another parabola that's been moved up 1, and it's wider, so it goes like this. Oh gosh, that's terrible. Excuse me. If you need to use a graphing utility to help you with this stuff, that's okay. But there we go, we've got it. Does everybody see that we do have, it looks like that any point in this region, in this domain, the x values are trapped between two constants and the y values are between two functions of x. Now, what are the x values that they're trapped between? How would you figure those out?
set the two functions equal to each other?
You could set them equal to one another. You could also just try and guess. Like I can just see by looking, one works, right? X is 1 works. And -1 also works. But algebraically, you could set them equal to one another and solve. So -1 to 1. And then let's look at the top one. The top one, I'm going to call that G2 of X. That's the 1 plus X squared. And then the bottom one, which is that one, I'm going to call that G1 of X. That is 2X squared. Okay, that is just the domain, right? This is capital D. So the double integral over capital D of this surface f of x, y with respect to area, since this is type 1, will be the integral, double integral. So integral from -1 to 1, and then integral from where to where?
To G2 of X minus G1 of X.
Yeah, so we're going to put 2x squared down here, right? Yeah, and let's just put 1 plus x squared up here. See, our limits of integrations involve variables. This is the first time this has probably ever happened to you. Normally our limits of integration are numbers, but now our limits of integration are functions. Now the f of x, y is the surface, which is this, x plus 2y. And here we have no choice. You must go dy for the inner and dx for the outer. I'm debating right now whether or not I should mention this now or after. Let me write this down. Do not copy this. What do you think? What did I do there? Do you think I'm allowed to do that? Can you all see what I did?
So you cut the equation in half and then doubled it so that you don't end up with an answer of 0.
Potentially it could be 0. But instead of going from -1 to 1, I went from 0 to 1, right? And then doubled the answer because these two regions are symmetric. Do you think I'm allowed to do that?
No,
Why not?
because the function above it can vary.
Yeah, see, so here's the thing. This is just the region on the ground. This is not the surface above it. If the surface above it is symmetric over that y-axis, then we could do this. But we have no guarantee that the surface above it is symmetric. Maybe we should look at the picture. So here's the ground, right? Here's our domain on the ground. Here's the domain in 3-dimensional space. If we look at the surface above this, do you see that it is not symmetric? If I look at the solid below this thing, can y'all tell that on one side it's higher than the other? Can y'all tell from that picture? Looks like on the right side this goes higher than this side. So if we just cut it in half and double this, we're doubling this volume, but that's not the same as the volume on the other side. So because there's no symmetry in the surface above, I can't do that. So just be careful, all right? Don't try, that's something in Cal 1 you could do that, or Cal 2 that you could do, but here, danger zone, don't do that. All right, so how do we do this? All right, so this is going to become an integral -1 to 1. Now, antiderivative. With respect to y, we should get xy plus y squared. That's the antiderivative of this with respect to y. Now we're going to evaluate that, watch this, at y equals 2x squared and y equals 1 plus x squared. And then after we do all that, we will go with respect to x. Now this becomes the integral from -1 to 1. And then I have to plug in two things. And then go with respect to x. All right, so first plug in y. So x, and then y is 1 plus x squared. And then plus y, which is 1 plus x squared, but then squared. And then plug in 2x. So x times, I'm sorry, 2x squared. Plug in 2x squared plus, and then we have 2x squared squared. And now we have a new integral that has nothing but x in it. All right, let me try and clean this up. This is going to be x plus x cubed plus 1 plus 2x squared plus x to the 4th minus 2x cubed minus 4x to the 4th. So I'm just cleaning this all up algebraically. Let me put this in descending order, highest power of x down. So -3x to the 4th. That should take care of those two. X cubed, so I've got minus x cubed. That should take care of those two. Plus 2x squared. Plus x plus 1. Dx. And now we're back in Cal 2, right? And so at this point, I'm going to say equals ... And you can figure that out, okay? The only thing that's new here is this limits of integration that are functions. Questions? Everyone doing all right? So if you were to finish that problem off, you would be finding the volume of that solid right there. So this is a different problem. Same thing. I'm just going to show you the region, and then we're going to set up the integral, but we're not going to evaluate the integral. So you first put y equals 2x, which is this line, and then y equals x squared, which is this curve. Now, technically, this parabola goes this way and this line goes like that, but it's the region between them, which has to be this. And so you can see that it goes from 0 to 2, right? And then you have a top function, which is your y equals 2x, and your bottom function, which is y equals x squared. So let's see. I'm gonna call on somebody here. We'll go backwards in the order that you appear on my participant list. So Terrence, how about you? You want to tell me what this integral, double integral setup is going to be? So what are my limits of integration here?
Okay.
It's type 1, right? Like your x's are
It
stuck
is.
between two numbers and then your y's are stuck between two functions.
It is type 1, so
Yep.
that the first two bounds would be 0 to 2, right?
Yes, sir. And then these bounds,
Would be y equals x squared
on the bottom,
to
yeah,
y equals 2x.
2x on the top. Now, yeah, you can write y equals here if you want. That's not a bad habit to do. It's up to you. And then what goes in here? What's the integrand?
The function, right?
Yep. Hmm.
X squared plus y squared.
That's it. There you go. So there's your setup. So you first integrate this with respect to y, and then plug these two things in for y, and then integrate that with respect to x, and then plug in 0 and 2 for x. So is it okay if we just do the setup, or do y'all want me to go further? Setup okay or no? Go further? I'm seeing yes, setup okay.
Yeah, I mean, it feels just kind of like a logical next step to integration.
Yeah, let me write the next step and then I won't actually do it. The next step would be the actual antiderivative of this with respect to y. And then we would replace y with x squared, y with 2x. After we do all that, right, 2x goes in here for y here, and then minus x squared in here for here, and here. Clean all that up and then integrate that with respect to x. And then go 0 to 2, right? Okay. All right, I'm just, oh, shoot. I didn't mean to do that. I meant to do this. I'm just going to take this and copy it and throw it into the notes here, just so it's here. Any guess what a type 2 region would be? If a type 1 region is x is between two constants and y is between two functions of x, what do you think a type 2 would be?
Would it be just
Would
the
either-
opposite?
Yeah, the opposite, right?
Right.
And
Yeah, so this is a type 2 region here. Is that your y's are between two constants, we call them c and d, and your x's are between two functions of y. So that's what this says. Your y is stuck between two constants c and d, and your x is between two functions of y. Then the only difference in the double integral is that now the y's have to go on the outside. The y stuff has to be on the outside, and then the x has to be on the inside. And it's the exact same thing. So here's an example. We'll get this one set up. We start out with the region. So I'm gonna draw my region here. Okay, y equals x minus 1 is a line. It has a y-intercept of -1 and a slope of 1. Y equals mx plus b, right? So we know that that looks like this. And then this one, oh, whoa, what's this? Isn't that a parabola that opens sideways? It is, right? It's a parabola that opens sideways. Let's just plug in some values of x here and see what we get. If x is 0, what's y? If x is 0, you get y squared is 6, right? Which means if x is 0, y is going to be plus or minus √6. That means I have like plus √6 minus √6. If x is 0, those aren't symmetric. Hold on. I don't know, something like that. Can anybody tell me where it would hit the x-axis? Why don't you just let y be 0? solve for x?
-3.
-3. And it opens up like this. Opens to the side like this. Do y'all see why this is not a type 1? You'll see why it's not type 1. You're like, especially like right in this region right here. Your y's are not stuck between two functions of x. Your y's are stuck between the same parabola. So it makes most sense to look at it this way, where your x's are trapped between two functions of y, and then your y's are trapped between, well, we need to figure out, the y's would be trapped between that point of intersection and that point of intersection. This would be our C and our D. Why don't we get our intersection? How do we do that? How about we solve this for x and solve this for x? So here I just moved added 1 to both sides. Here I moved the 6 over, subtracted 6 and divided by 2. And then just went ahead and did the 2 on both of those. Now that they're both solved for x, I can set them equal to one another. So to find the intersection, I set y plus 1 equal to 1/2 y squared minus 3. And that's a quadratic equation I have to solve for y. So I'll move quickly through this. I'm going to double each side just to get rid of the fractions. I'm going to move everything to the right. And then luckily for me, I can factor this. So I know that they're going to hit here at 4 up here, and this down here is -2. Any questions? So now what we'll do is this. The double integral over this domain of the surface with respect to area, because it's a type 2, should be the double integral with respect to y on the outside and x on the inside. My restriction on y is -2 to 4. Now, what's the restriction on x? In the previous problem, it was the restriction on y, and so it was the top minus the bottom, right? Top one, the top curve, sorry, not top minus bottom. This top limit was the top function, and the bottom limit was the bottom function. Here, we're looking at a function that is on the left and right. So the one on the bottom is the one on the left, and the one on the top is the one on the right. But those have to be functions of y, not x. So this right here has to be h2 of y, and this one right here has to be h1 of y. Do we know what those are? How about this one right here? What is this line written as a function of y?
Y plus 1 equals x.
Y plus 1, right? This is it right here. X is equal to y plus 1. So this is just y plus 1. And then this one, h1, this is the parabola, is this equation solved for x, which we already know is 1/2 y squared minus 3. So that means my lower limit of integration is x equals 1/2 y squared minus 3, and my upper limit of integration is y plus 1. And what's the integrand? Well, the integrand is just this, right? There it is. All right, I'll go one more step, and that's it. The next step, are there any questions? Antiderivative of this with respect to x would be 1/2 x squared y. Treat y like a constant. Evaluating that from x equals 1/2 y squared minus 3 to x equals y plus 1. Then we'll go dy. So I'd first plug in for x, I'd replace it with this, plop it in there, figure out what that is, then subtract from that what I get when I replace x with this. Look, the algebra is going to suck, okay, but it is just algebra at that point. Equals ... On your final, I'm probably going to be giving you problems. Like any of these problems, I'm probably just going to ask you to set up the double integral. Just like set it up. That's it. You're done, move on. Because really at this point, it's just, I mean, it's not hard stuff at that point. It's just being able to get the region, make sure you're using a proper order of integration, proper limits of integration. The rest is very mechanical. All right, I'm going to move on. This is a good problem. Find the volume of the tetrahedron bounded by x plus 2y plus z equals 2. What is that? What is this geometrically? What does that look like? It's a surface, right? What does it look like?
Plane.
It's a plane. The normal vector is 1, 2, 1, right? So that's a plane, right? So we have a plane. So find the volume of the tetrahedron bounded by that plane, x equals 2y, x equals 0, z equals 0. Okay, what? Okay, let's try and draw this three-dimensionally. All right, let's start with the easy stuff. X equals 0 is really the YZ plane, isn't it? If this is X and this is Y and this is Z, then we're talking about this kind of wall right here, okay? That's X equals 0. Z equals 0 is the XY plane. That's the ground, isn't it? It's the ground. So that looks like, this is going to start to look really bad. Okay. X equals 2y. X equals 2y. Okay, let me write that a different way. Y equals 1/2 x. That's also a plane, right? But in two-dimensional space, isn't that a line? This is x and this is y. Isn't this just a line with slope 1/2 like this? But imagine that on the ground here, it'd be like this. That's what it'd be on the ground. But because it's in three-dimensional space, it's actually a plane. Okay, yeah, you see this starting to look like a real disaster, isn't it? And then we have this plane. We're trying to find the volume of all of those, like where the volume of the tetrahedron enclosed by all of those. So how can I figure out where this plane is? Well, one thing I could do is I could figure out where it hits the X, Y, and Z axes. So like to figure out where it hits X, I just let Y and Z be 0. If Y and Z are 0, then it hits at 2. So let's say that's X equals 2. If I want to know where it hits the Y axis, I let X and Z be 0. And if I solve for Y, I get 1. And if I want to know where it hits the Z axis, then I let X and Y be 0 and we get Z equals 2. So we have this tetrahedron, or sorry, this plane that would cut through like this. Boy, it's probably pretty hard to see what this is. I'm going to try and draw another picture. Let me do it a little bit different. I'm going to go like this. I'm going to let this be X, and this be Y, and that be Z. It hit the X-axis at 2, hit the Y-axis at 1, and the Z-axis here at 2. So this was, that plane came in like this. And then we had the other plane, which was the line on the ground that went like that. That plane cuts through. Remember, this plane goes up and down. Boy, it's hard to see it, but that plane would cut through somewhere in here. I think it's hard to see. It's definitely hard to draw. So this is, that's about here. You know what? I have a good way we can do this. Let me get this, copy it. How am I doing? 10 minutes. Let's do this. Let's try and figure out what D looks like, which is the ground. Okay, let's just figure out what the ground is. Okay, so X equals 0 is this right here, right? That's X equals 0 is like a line in two-dimensional space. That's X equals 0. Okay, X equals 2Y. Let's do this one. That's a line that goes like this. That's Y equals 1/2 X. Z equals 0 is the actual XY plane that we're looking at. But what about this? What would that one look like in two-dimensional space? Well, on the flat sheet of paper, wouldn't Z be 0? If Z is 0, so in 2D, we want to look at 2D, then it's just this, right? Let Z be 0. And then let's solve for Y. So I move the X over, divide both sides by 2, I get this. This is a line that has a y-intercept of 1. And has a slope of -1/2, so it comes down like this. So the domain on the ground that contains both X equals 0 this line and this line is going to be this region right in here. That's our D. Now, the surface above it, right, the thing that's above it, the tetrahedron that's above it, is dictated by this plane. So let me take you back to that picture we had to see if this makes sense now. Here's the region in two-dimensional space. Here's that region on the ground. Here's the plane that's above that region. And so the solid we're talking about is the solid below that down to the ground. And then I'm going to pull the plane out of here. There we go. Make sense? So how can we describe this region here? Let me zoom in on it a little bit. I think it's a type 1, right? We have our x's are stuck between, the x's are stuck between here and here, and then our y's are stuck between two functions of x. So I do need to see where these hit each other. I think it's obvious from the picture 0. My x is going to be between 0 and something here. To figure out where they hit each other, I have to set 1/2 x equal to this. So if I set those equal, 1/2 x equal to -1/2 x plus 1, and move that over to the other side, you get x equals 1. They hit each other at 1. So this would be 1. The y is stuck between, let's see, the green line's on the bottom, so this is 1/2 x. And the red line is on the top, and that's -1/2 x plus 1. Those are our limits. So this is our type 1. So I'm pretty sure from here I can set up the double integral. The only real other thing I need to do is to take this equation and solve it for z, so that way it's a function of x and y. So just move the x to the other side, the z, the 2y to the other side, and solve for z. This is our surface above that domain. And so that should be everything. Double integral, it's a type 1, so the x goes first, then the restriction on y, then the function of two variables, and then y first, or y is the inner, and then x is the outer. This should give us the volume. Okay. That was a little tricky. Do you have any comments on that one?
What is that one on top in the red? 2 minus d?
2D, sorry, I was saying two-dimensional, sorry, in two-dimensional space.
Oh,
2 dimensions. In 2 dimensions, this plane, if you project it down to the ground, z is 0, and it creates a line. It's basically in this picture, it's where the plane hits right here. That plane comes in and intersects the ground in a line right there. You can see it, yeah. That's from the bottom. You can see the line.
oh, okay.
All right, it's 2:36. I think that I'm going to have to say that's it for now. We still have 1, 2. Well, you know, I can do this one. Let me do that, and then we'll move on. There's still at least 3 or 4 more examples. I'd say you can definitely do the homework for 12.1, but 12.2 you can get started with it. This formula right here is going to be used quite a bit later. It's actually a really cool formula because it's simplicity, but it's very intuitive also, I think. If you look at what we've done today, we've said if we have in three-dimensional space, say this is X and this is Y and this is Z, that if we have some domain on the ground here, D, and then above it, we have some surface, whatever that surface is, right? Call this f of x, y. Then the double integral will give us the volume underneath of this, right? Underneath this. But what if I tell you that that surface on top isn't just any function? What if I tell you that function is the constant one function? So it's just flat. Okay. So it's 1 unit high. Oops. So it's, what if I tell you that the distance from here to here is 1 and it's just flat, a flat plane? Wouldn't it just be that image of D just up here? Wouldn't it be just D up here? Now, the volume of this would be the area of D, whatever the area of D is, times 1, wouldn't it? Because that would be how tall it is. But the area of D times 1 is just the area of D. Which means that if you ever do a double, this is the key right here. If you do a double integral over D of 1 dA, then what you get is the area of D. There's something like this in Cal 1, but we don't really talk about it in Cal 1. In Cal 1, it would be like this. What if I told you to take a function on the interval a, b, but I now tell you that that function is 1 unit high and it's just constant 1, right? What if we look at that? And I ask you now to find the area below this. That area would be just how wide this is, right? How wide is this? What's the distance from here to here?
E minus A.
E minus A. So that's the length of the interval, isn't it? That's the length of the interval AB times, now what? How tall it is, right? But how tall is it? 1, right? Times 1, which would just be the length of the interval AB. So back in Cal 1 or Cal 2, we could have said this: the integral from A to B of 1 dx is just b minus a. So the integral of the constant 1 function gives you the length of the interval that you're integrating over. Here we're saying that the double integral of the constant 1 function over some domain gives you just the area of that domain. Instead of length of interval, because here your domain is an interval, so this just spits out the length of that interval. Here your domain is an area, so the double integral of 1 gives you the area of that D. Now that may not seem very useful, but it actually is going to be very useful. All right. Okay, we're out of time. So any questions? We good? 12.1, start 12.2, and then we will get into 12.3, which we're going to do polar coordinates. That's coming up next. So we're going to do double integrals and polar coordinates. Then we'll get to triple integrals. Have a good day, everyone.
Thank you, sir.
I have a quick question.
Yes.